Welcome back to the course of structure analysis. In this lecture, we are going to analyze a proper cantilever beam, which is having a sinking at the free end. So this is a problem. Cantilever shown in the figure, it is having a rigid support, which is 10 mm below the free end. We are going to analyze that beam as shown in figure. And then EI here is 150000 kilonewton meter square. So this is a cantilever beam which is shown, and it is also having a support at this B1, but here to this free end and to this rigid support you are having a gap of 10 mm. So here you can call this as a sinking one, sinking of this support at this free end. So EI throughout this entire beam is given as a constant. So you are going to analyze this beam. If analyzing means we are going to find the reactions first. Before finding the reactions, we'll first determine the degree of static indeterminacy. So for that, we'll calculate the number of reactions here. So A is a fixed support. We are having a 3 reactions. One is horizontal, vertical, and moment. And at B also, you are having a vertical reaction. Therefore, the total reactions are 4. And the static equilibrium equations here are 3. That is sigma fx, sigma fy, and moment xy equal to 0. Now the degree of static indeterminacy is number of reactions minus static equilibrium conditions. So that is 1. Now we are going to balance the forces. So for balancing forces, we take sigma fx equal to 0. So as there is no horizontal loading, external loading, so here HA will be equal to 0. And sigma Fy equal to 0. So that means Ra plus Rb will be equal to this 40 plus 60, that is total 100 kilonewton. So this is another equation. Now we are going to choose a redundant force. This is a this is a beam that has been given to us. So now this indeterminate beam, which is having 1 degree. So to solve that, we make this entire indeterminate to be beam divided into 2 parts. So one part is we are going to take a simple cantilever beam with a 2-point load. So here this support we are removing. Just we are making this simple cantilever beam which is having only the external loads. And now second part is with a cantilever beam with a point load at this B support, this B end. Now this vertical reaction RB is treated as a redundant force. Now we are going to calculate the downward deflection for this cantilever beam. So this is the first part, which is having a 2-point loads here. As there is no support sinking 10 mm below the free end, now we are going to use the deflection formula for this 2-point load. So to calculate the deflection at this free end, we are going to calculate the deflection due to this 40 kilonewton as well as the deflection due to this 60 kilonewton. So together you are going to add. As this load is eccentric distance of 2 meter and 4 meter. Similarly, 60 kilonewton is eccentric for 4 meters and 2 meters. So due to eccentric loading, the deflection formula is WAQ by 3I plus WA square B by 2EI. So first I am going to consider only the 40 kilonewton load. So to this 40 kilonewton, A is 2 meters, B is 4 meters, and this is a deflection curve we are getting. As this is a downward load, you are getting a deflection to be downward only. And for the next case, you are having a 60 kilonewton, and here also the deflection will be in the downward only. So same formula we are going to use. But here we are going to change A and B values. So the deflection due to 40 kilonewton load is this one, and the deflection due to 60 kilonewton load is this value, this equation. Now together you are going to add and we are going to get the simplified value like this. Therefore, the delta here is 0.0177778 meters. So this is a total downward deflection due to this external loads, that is 40 kilonewton and 60 kilonewton. After calculating this downward deflection of part 1 cantilever beam, now we are going to calculate the upward deflection, and upward deflection we are going to calculate for this beam, for the same cantilever beam, but here you are having a vertically upward reaction, that is RB. So here the reaction is RB, and the upward deflection is due to this RB is given by delta 1. So this delta 1 is RB into L cube by 3A. Now I'm going to substitute the L value and EI value. The simplified version of delta 1 is this one. Now after that, we are going to calculate the reactions and moments. So before calculating the reactions, we are going to use the consistency condition. So here the consistency condition is, the net deflection is 10 mm. Therefore, the net deflection here is downward deflection minus upward deflection, that is 10 mm. Delta is downward and delta 1 is upward. So as we calculated delta and delta 1 values from in the previous slides, I'm just substituting the values, and I'm going to calculate the RB reaction, that is 16.2 kilonewton. As we know that RA is equal to 40 plus 60 minus RB. I'm just substituting the RB value here. Then I got RA as 83.8 kilonewton. So after getting this RA value, now I'm taking the moment about this B equal to 0. Therefore, I get the equation as minus MA, which is in anti-clockwise direction, and RA into 6 is plus, that is clockwise direction, minus 40 into 4, again anti-clockwise, and minus 60 into 2, again anti-clockwise. So by solving this, I got MA value as 222.8 kilonewton meter. So this moment is hogging in nature. As we got the positive value, so I'll keep this hogging nature in the same way. If I get the negative value, I'm going to change the direction of this arrow to the other side. So as it is in anti-clockwise, now I'm going to keep it in the clockwise. Then the nature will be in sagging in nature. So now as it is, I'm keeping, it is in hogging in nature. So this is how we are going to calculate the reactions and moments. Coming to the next slide, we are going to draw the shear force diagram. So to draw the shear force diagram for this beam, first we are going to take the limits. I'm starting from B to A. So here X is equal to 0 at B and X is equal to 6 meters at A. Now these are the reactions and moment values. And this is a sign convention. So towards this section, when we take the shear force to be clockwise direction, it is positive shear. Towards this section, when the force is in the anti-clockwise direction, then it is a negative shear, both the sides. Now I'm going to take the shear force in BC section. Now I cut the section in BC and this is an X distance. Now the shear force equation will be minus RB. Why? Because it is an anti-clockwise direction. The limits are 0 to 2. Therefore, from 0 to 2, the shear force will be negative and it is of 16.2 kilonewton. In next, I'm going to take the section in CD and which is of X distance from B. Now the shear force equation is minus RB and plus 60, which is from 2 to 4 meter. Now I get the shear force value to be 43.8 kilonewton, which is of positive value. Now I'm going to take the shear force in DA section. Now I'm going to cut here, at which is of distance X from B. Now I'm going to write shear force equation, that is minus RB plus 60 plus 40. So the limits here are from 4 to 6 meters and the shear force value is 83.8 kilonewton throughout D to A. After getting all the shear force values, in the next we are going to plot the shear force diagram. So the shear force diagram will be, first I'll write the values. So shear force in BC section, it is of negative 16.2 kilonewton and this is of CD section and this shear force value is of DA section. Now I'm going to take at B, it is 16.2 kilonewton and similarly at C, it is 16.2 kilonewton and which is of negative value. Again from 2 to 4, it is 43.8, which is positive. So I'm writing C 43.8 and here D also 43.8. And from D to A, I'm getting 83.8 kilonewton and it is 83.8. Now I'm going to join all these things. So this is how we are going to get a positive value. So C to B, it is negative of 16.2 kilonewton. D to C, it is 43.8 kilonewton positive. And D to A, it is 83.8 kilonewton positive. So this is a shear force diagram. And now going to the bending moment diagram. So these are the reaction values. And this is a sign convention for a bending moment. Now we are going to take a section in BC. So due to this sign convention, as the arrow is heading upward, so the bending moment equation will be plus RB into X, and the limits are 0 to 2. So when we substitute X is equal to 0, bending moment is 0. And at X is equal to 2, the bending moment is positive value of 32.4 kilonewton meter. Now next I'm going to cut the section in CD, so which is at a distance X here. Now by bending moment equation will be RB into X positive minus 60 into X minus 2. This distance I'm going to take the load to the section distance. That means total X minus 2 I'm going to subtract. So this is from limits 2 to 4. So when X is equal to 2, the bending moment equation is 32.4 kilonewton meter positive, and X is equal to 4. I'm having the bending moment value to be a negative, which is of 55.2 kilonewton meter. So that means in CD section, the bending moment value is changing from positive to negative. So that means I'm going to get point of contraflexion in CD section. In the next slide, we are going to cut the section in DA portion, so which is of X distance. Now the limits are 4 to 6. Now my bending moment equation is RB into X, which is of positive value, minus 60 into this X minus this this distance, and minus 40 into this X minus this 4, that is this distance. So this is the equation I have written. Now at X is equal to 4, I'm getting bending moment value to be minus 55.2 kilonewton meter. And X is equal to 6, I'm getting as negative 222.8 kilonewton meter. Now, as we know, already discussed in the previous slide, the bending moment sign convention has been changed in CD span. So I'm equating the bending moment equation to be 0 in the CD span. Now I got X is equal to 2.74 meter. So this is a point of contraflexion. In the next slide, we are going to draw the bending moment diagram. So these are the bending moment values at different points B, C, D, and A. And this is a bending moment where you are getting it as 0. Now I'm going to draw a beam. And at B, I'm having a bending moment 0. And at C, it is a positive of 32.4 kilonewton meter. And at D, I'm having of 55.2 kilonewton meter, which is negative. And at A also, I'm having a 2 to 2.8 kilonewton meter, which is of negative value. Now just I'm joining all these things. B to C positive and C to D it is negative, and again D to A it is negative. So this is a bending moment diagram, and the bending moment is getting 0 at X is equal to 2.74 meter. So this is a final bending moment diagram representing all the bending moment values as well as the where you are getting the bending moment as 0 also. What is the distance? So these are the textbooks and references. Thank you.